Hiya. So I had a question from Milena, thank you. This was on the sample assessment material. This is question 9 on the mechanics bit. Okay, so it's this one there. All right. Okay. I'll read out the question too. So you've got a beam AB, there it is, of mass 20 kilograms, length 3 meters, smoothly hinged to a vertical wall at one end A. Okay, so this beam is hinged to the wall there. But sometimes I do this to indicate that that surface is a wall, okay, as opposed to just a vertical rod, for example. Okay, just it helps me. All right. The beam is held in equilibrium in a horizontal position by a rope of length 1 meter. Okay, it's 1 meter rope. One end of the rope is at a fixed point C, so there, as on the diagram, on the wall just vertically above A. The other end of the rope is fixed to point D on the beam, so the angle ACD is 30 degrees. So there, 30 degrees. All of that is shown in the diagram. The beam is modelled as uniform. Right, so I'm going to put in the weight of the beam there, okay? So uniform, and the mass 20 kilograms, so 20G. And the rope is modelled as a light, inextensible string. Using the model, find the tension in the rope. Okay, find the tension in the rope. So I need to use that one now. So this is what we need to find. Okay. Right. Tricky question. Okay. Tricky question. It's a moments question. Hopefully you realise that. Okay. So let's take a moment to think about this. Done. Okay. Where should we take moments from? That's for you to think about. I'm going to take moments from A. Why did I take moments from A? Because part B of the question says find the direction of the force exerted by the wall onto A. So that means is something interesting is happening here. The wall is exerting a force on this beam. We're not really so sure what that is yet. So the best thing to do is try to just ignore it by taking moments about that point. Then all we need to do is just worry about the other forces, which are the weight, obviously, and the tension there. Okay. So take moments about A. Tension then. Well, a force is just that, isn't it? And then we multiply that by the perpendicular distance. The perpendicular distance of this force is this distance here that I'm marking on there. We've got to work out that distance. All right. How are we going to do that? Well, if I use that right angle triangle, if that's 30 degrees, that's 90 of course. I'll put in here, that must be 60 degrees. And it'd be handy to know this length here, AD. I can do that by using this right angle triangle here. Okay. And I'll put it up here. AD is equal to 1 multiplied by sine 30 degrees. Okay, 1 multiplied by sine 30 degrees. So 1 times sine 30, which is equal to 0.5 meters. Okay, so that length there is 0.5 meters. All right. Why don't I just write it on? 0.5 meters. So this length there, that is opposite 60 degrees. Okay, so that's going to be 0.5 sine 60 degrees. Okay, that's the tricky bit. Okay, so that's the moment by the tension. Okay, from A. All right. Then the easy bit is the 20G. Okay, because that is just going to be force 20G multiplied by the distance. Distance, of course, is just going to be that which we know is 1.5. Yeah, because all of that is 3. This bit here is halfway. That's 1.5. This bit is also 1.5, so it's 1.5. Okay. In terms of moments, the tension is going to have a anti-clockwise moment about A, and then 20G is going to have a clockwise moment. They're going to balance each other out, aren't they? So you could say that subtract that equals 0, or you could say that equals that, because it's an equilibrium. Yeah, and so these two must be equal. So that's how we're going to work out what T is. T is the only unknown, so we can now go ahead and do that. So sine 60 degrees, that's root 3 over 2. Root 3 over 2 times a half is root 3 over 4. So root 3 over 4t is equal to, then 20g, that's going to be times it by 1.5, 30G. All right, and then so T must be equal to, times by 4, 120 G over root 3. And I can't do that without a calculator. Here we go. So 120 times 9.8. Always use 9.8, remember? 9.8 is what you should be using. You know who I'm pointing to. Ben, Topaz. Yeah. Divided by square root of 3. Okay. Right, so that's 678.96 something, right? Since G is involved, I'm going to put it as 680, okay? So 680 newtons, and that's, remember, that's two significant figures. Always use two significant figures when G is involved, right? Thank you, Mr. Calculator. So that's the first bit, all right? Got to remind myself what the second bit is. The direction of the force exerted by the wall on the beam at A. So it doesn't actually ask for what the force is, the magnitude is what it would be. It asks for just the direction. And it's worth 6 marks. 6. That was a Joker reference from The Dark Knight. I think you know what scene I'm talking about. Anyway, yeah. So it's not going to be simply, that is it. That would be a 1 mark question, yeah. So it could be a bit more complicated, okay? So what you can assume from the number of marks is that the force exerted by the wall is going to be at some awkward angle, okay? It's not going to be purely horizontally or vertically. It's going to be a mixture of the two. So what we need to do is consider what the horizontal component would be. I'm going to call that X. And what the vertical component would be. I'm going to call that Y. Okay? I'll say a point about that in a minute. You might have said, well, why did you choose X that way and Y that way? Okay, I'll cover it now since I've asked the question. Okay, so what do you mean? Why have you put X that way, Y that way? No, I know none of you talk like that, but you know. Anyway, just imagine that was my Cartesian axis there. I always use right and upwards for positive. Just helps, okay. If any of them are wrong, we'll find out in the due course of time, okay. So what we're going to do is we're going to resolve both horizontally and vertically, and we're going to find what X and Y are, okay. I'm hoping I can do it in this space here. So horizontally first. What's going on there? So X, what's that going to be equal to? Well, obviously we don't count 20G because that's got no horizontal component. Because I've got X towards the right, the tension is effectively towards the left, and because it's in equilibrium, they're going to balance out, so it's going to be equal to something multiplied by T, isn't it? Okay. What is the horizontal component of the tension? Look at this right angle triangle. So T, and then it's going to be that bit there, isn't it? Which is adjacent to 60 or opposite 30 degrees. Okay, let's go for opposite. I prefer sine. Okay, I always prefer sine. Okay, so T sine 30 degrees. Okay, well, we can work out what that is, can't we? So you got that's T, so times that by a half, so 60G over root 3. Yeah, 60G over root 3, and if we want to we could work that out, but we don't need it, okay. But just use the exact answer. Do not do that, you know, whatever you do, don't write down, oh, it's 340. It's not, is it? That's a rounded figure. Okay, so you keep the exact figure because we'll have to use that in another calculation. Can I squeeze vertically down here? I'm going to have a go vertically. So Y is equal to, well, obviously opposing it is the 20G. Now, since I've got Y going upwards and T is going upwards, you'd have the Y component plus the tension in the string is equal to the weight component. So what that means is, if I bring the tension to the other side of this equation, I'm going to have 20G subtract the tension component. I'm hoping it's obvious, but since we use sine 30 degrees there, it's going to be cosine 30 degrees there. Okay, but if you just check, there's the tension there, and we want to have this bit there, which is adjacent to 30 degrees, so cosine 30. So here we go, cos 30 degrees. Okay, so can I do this in one line? Well, I've got no choice really, have I? Okay, so cos 30 degrees is I'm going to do it here, then mug it off if you don't mind. Okay, cos 30 degrees is root 3 over 2. Okay, and that times by root 3 over 2 is going to be 60g. Would you agree? 60g, so that will be just 60g. Yeah. 20g subtract 60g is negative 40g. Do not panic with the negative. Okay, negative 40g. All right. Since you're happy with that, I'm going to rub that off. Okay. What that means is, I'm looking for my blue pen. What that means is, okay, that the horizontal component is, because it's positive, it is towards the right, but the vertical component, because that's negative, it's actually downwards. It's actually downwards like that. So the force looks like this. Lord Vader smiles whenever I mention the force. Yes, he is. He's wearing a helmet. You just can't see him smiling. He's smiling. Okay. So you've got x there. And because that's negative, it means it's downwards, like that. So the angle we're looking for is that, which is going to be an angle below the horizontal. Okay? So what means the force is acting that way. Let's just take a moment to think about why that is. So I didn't do that on purpose. Take a moment. It kind of slips out. Okay. Let's take a moment to think about why that is. Okay. So you've got this. Yeah. You've got this wooden beam, okay, it's attached there via this string. Suppose it slips. What's going to happen? It's likely the wooden beam will do that. You agree? Okay. If it slips, it's likely to do that. Okay? But it's not. Because there's a force there that's keeping it in a horizontal position. Because it's not doing that, there must be some force acting on the wall, from the wall to the beam, keeping it downwards like that. Okay, see what I mean? It would slip like that, okay, because it's attached to the string, but it's not. There's some force exerted by the wall that's keeping it horizontal, so it must be downwards. That's trying to explain to you why it's a downwards force. Okay, if you didn't understand that, not to worry. You just need to do the maths and get the actual values. Right, now let's use trigonometry to work out that is. So I can just squeeze it in here. Tan theta is y over x. I told you I could squeeze it in. So you just do that divided by that, don't you? I can write that in as well. So ignoring the negative sign, okay, because if I'm drawing it like that, I know my answer is going to be an angle below the horizontal. So 40g divided by that, well the g's will cancel, of course. 40 over 60 is 4/6, that's 2/3. And then over the root 3, so that's going to be 2 root 3 over 3. 2 root 3 over 3. And just need the calculator again to work out what that is. Okay, and check. Let's put it in degrees mode. Now it's in degrees. Okay, and then what we're going to do is 2 root 3 divided by 3. Yep, so 2 root 3 over 3. Inverse tan of that is 49.106 something. You agree? So I'm going to write that as 49 degrees to two significant figures. There we go, 49 degrees. Okay, that's it. Let's read the question again, because we might not be finished. Question says, the direction of the force exerted by the wall and the beam is 49 degrees enough? No, think about what I was saying, because if you leave it like that, it could be upwards or downwards, couldn't it? Okay. So the best thing to do is write 49 degrees below horizontal. And I'm amazed I fit all of that onto one board, if I'm honest with you. Kind of impressed. Alright, so that's that. Part C. If the rope were not modelled as being light, state how this would affect the tension in the rope. Explain your answer carefully. What does that mean, explain your answer carefully? What it means is, don't just say tension will increase. Okay? It wants you to explain why tension will increase. Okay? Well, the tension is going to increase, but it will increase the further up the rope you go. Let me explain why that is. I brought a prop along with me. This here is a rope. Okay? It's got mass to it. In this, it's modelled as light. If it was light, that means there's no mass. I wouldn't actually feel. It would be like this, dangling nothing, which looks weird. Okay, but I won't. I've attached something to it. Since I'm not allowed to use this outside, I want to make good use of my cycle helmet. Here's my advertising cask. Okay. They're very good, and they're actually quite light. Okay. Well, I've attached my cycle helmet to this. Okay. All right. Do you think there's much tension in the string between my finger and thumb here and the actual helmet? What do you think is happening to the tension in the rope as I go further up? What do you think? Well, what's happening is, from here to here, the rope has got to deal with not only the mass and hence weight of the helmet, it's got to deal with the mass of all of that and the weight of all that. Okay. If I just had this bit there, there's a lot less rope there, so there's a lot less mass and a lot less weight, isn't there? Okay. Now imagine this was a heavy chain, metal chain, whatever you want to call it. Okay. Yeah. Can you see that the actual mass and the weight is going to increase? So the answer is, the more rope you've got underneath where it's been suspended from, the more mass there is and the more weight. Okay. I'll print off the mark scheme as well because it could sound confusing if you just read it. It says tension will increase as you move from D to C. It's basically saying as you go up the rope. I would say something like as you move further away from the point at which it's suspended, D. Okay. Since each point of the rope has to support the length of the rope below it. That's the explanation I just gave you. Okay. Because each part of this rope has got to suspend everything that's below it. Okay. So that's that. Okay. Right. Let's do part D. It's a bit of a wordy one, isn't it? The rope is now removed and replaced by a longer rope which is still attached to the wall at C. It's now attached to the beam at G, where G is the midpoint of AB. Incidentally, we sometimes use G to represent the centre of mass, centre of gravity, it's sometimes called. So what they're saying is that instead the rope is doing this. Okay, instead the rope is doing this. It's attached to there. They call that G. So I'm going to rub out this bit here. No longer got that. Okay, size might make a bit of a mess. I did a better job on that than I thought. That's not 1 metre, of course, it's longer. Okay. We don't need that anymore because that's irrelevant, the 0.5 metres, and that's irrelevant as well. Okay, so that's what we got. Okay. You might be thinking, why is this a 2-mark question? It's actually quite simple. Okay. So what you've got is this. It's still a moment's question, okay, as we had from earlier. Okay. But what we're going to do is something very clever. As always, we're going to take moments about G. Okay, we're going to take moments about G. Just take a moment to think about that. Sorry, I've used that a third time. I know. So the first time I did it on purpose. The third time, absolutely not. The second time just slipped out of the circuit. Yeah, that's what we're going to do. We want to take moments about G. Why do you want to take moments about G? Because then we can ignore the weight, 20G, because it passes through it. We could also ignore the tension as well, because see the tension as a force, it passes through G, so we can ignore both those. The only forces that we're going to look at are this two and this two, but hang on just a minute. The X force, that horizontal force, that also passes through that. So actually no, we only have this force. The force Y, that vertical component from the wall, that's the only one we were going to consider. And that force is a distance of 1.5 metres away, so 1.5 y. That's the only force. Hang on again, the whole thing is in equilibrium, so that means that y must be 0. Y must be 0. What does that mean if y is 0? It means that that's no longer there. You've only got the horizontal component. And that answers the question 4. You put therefore, the force exerted by the wall on the beam at A now acts horizontally. That is it. That is it. Okay. Hope you enjoyed that question, okay? And hope it was useful to you. Right. Bye-bye for now.